Well, good morning, everybody. Today we are learning 3-3 transforming functions, day 1. And this is a lesson where you're able to graph any functions or equations without plotting points. But before we do that, one of the most important thing is you have to learn how to graph with the most basic methods, which is a review of graphing an equation by a table of values. So let's take a look at that. First, I see that this equation is y equals x minus 3. Most of you have learned how to graph this using slope-intercept form, like y-intercept and slope, and then you graph it without the table. But nevertheless, in case if you never have graph using slope-intercept form, or you just don't like that method, you're able to use the most primitive or basic way, which is a table of values. So when you graph an equation with a table of values, we usually pick numbers around the value 0. So we're going to pick the 5 values, -2, -1, 0, 1, and 2. And then we're going to replace the x with these 5 values, and then we want to subtract 3 and see what are the 5 y values. Well, let's take a look at x is equal to -2. When x is -2, you replace the x with the value -2. So -2 minus -3 is equal to -5. You could use your calculator or you could use mental math to find that value. So we're going to plot -2 comma -5. So -2 comma -5 is somewhere down there, and my graph does not really have a extended y-axis, so I'm going to extend it -4, -5 here. So to plot -2, -5, I start from the origin, I go to the left 2 and down 5, and then this is my point. Next, when x is -1, I'm going to replace this x value with -1. So -1 minus 3 is -4. So when x is -1, y is -4. So I'm going to start from the origin. I move left 1 and down 4. And then this is the second order pair. Let's keep going. When x is 0, you're going to replace this x with 0. So 0 minus 3. And it's -3. So 0 comma -3, you do not go left and right, but you go down 3 units. So this is 0, -3. When x is 1, you replace the x value with 1, so you do 1 minus 3. So 1 minus 3 is -2. So 1 comma -2, you're going to start from the origin, move to the right 1 unit, and then go down 2 units. At last, when x is 2, you're going to replace this x value with 2. So you do 2 minus 3. So 2 minus 3 is going to be -1. So 2 comma -1, you start from the origin, you move to the right 2 units, and then go down 1 unit. You notice that this is a straight line, it's a slope-intercept form, and we're going to use a ruler to connect all these 5 points together. And then this is your graph of y equals x minus 3. To verify that your answer is correct, easy, you could use slope-intercept form. You notice that the y-intercept is -3, and then your slope, since there's no numbers in front of the x, there's an invisible 1. And then if you were to make it a fraction, it's going to be 1 over 1. That means you move 1 up and 1 to the right. So to verify that, you look at the graph, I see that this line touches the y-axis at -3, and then for every single point after that, you move up 1 to the right 1, up 1 to the right 1. So that's how you could check that your answer, this graph, is the correct graph for y equals x minus 3. Well, in 3-3, Transforming Functions Day 1, we're going to learn some shortcuts of graphing functions without a table of values. This is very similar to an art class or like a shortcut class where you're able to to graph something without spending too much time or calculating too much math. So before I start, there are something called a parent functions, and in this lesson there are 3 parent functions I want you to learn. The first one is f of x equals x. We call it a linear function, which we saw a lot in chapter 2 or topic 2 and at the beginning of topic 3. Now this one we have not seen it in the past, but it's called g of x is equal to x squared, and it's called a quadratic function. So anytime you see a second power, we use the word quadratic in math to indicate that something is raised to the second power. And then lastly, we have an absolute value. So in the past, in middle school, you have learned what's absolute value of any number. It's always positive. So whenever you have an absolute value of x, we call it a absolute value functions. So these are the 3 parent functions that you're going to learn, and you're going to learn how they look like. Think of each function, it's like an individual. You have to learn their name, first of all, linear, quadratic, and absolute value, as well as how they look like, so you know that the shape of each individual, or each function in this case. So we're going to sidetrack, and we're going to graph, just for one time, you're going to create a cheat sheet of finding out how are these three parent functions look like. So we're going to move on to this page right here. Now, first of all, what is a parent function? So parent function is the most basic function with the least number possible. Like, for example, in the past, you learned that linear function is y equals mx plus b. You could create a lot of equations like y equals 2x plus 1, y equals 4x minus 5, y equals 1/2 x minus 7, y equals any number x plus or minus any number. And there's millions of examples. But at the end of the day, the most simplest, the easiest, the shortest linear function would be just y equals x. And you cannot make anything simpler than y equals x for a linear function, okay? So that's why this is called a parent function, because all the functions that we could create an example from come from this parent, just like our mom and dad, right? So this is a linear function, the most simplest function. Y equals x is the most simplest parent function for this type of linear function. So how do I graph this? Well, let's use a table of values. Well, it says that whatever x is, your y value is the same. So when x is -2, your y is -2. When x is -1, your y is -1. When x is 0, your y is 0. When x is 1, your y is 1. And when x is 2, your y is 2. So you're going to plot this -2, -2. You go left 2, down 2. You plot a point. -1, -1. You go left 1, down 1. You plot a point. 0, 0. That's easy. It's right at the origin. 1, 1. That's also easy. You go to right 1, up 1. And then at last 2, 2. You go to right 2, up 2. So this is a parent, the graph of a parent function, and it consists of these 5 points. And what we're going to do is we're going to highlight or make these 5 dots larger. So I'm going to use a marker. So these are the 5 dots that you kind of have to memorize for this particular linear function, this parent linear function, okay? Well, let's move on to quadratics. So quadratics says that whatever x you have, you multiply by itself. So when x is -2, you're going to do -2 times -2. So -2 squared is -2 times -2, which is +4. When x is -1, you raise -1 to the second power, which is -1 times -1. And remember, negative times a negative is positive, so 1 times 1 is 1. And when x is 0, so 0 squared, so 0 times 0, it's going to be 0. When x is 1, you do 1 squared, so 1 times 1 is 1. And it's okay that some of these y values are the same, and that's totally fine. And at the end, when x is 2, you raise 2 to the second power, so that means it's 2 times 2, which is going to get you 4. Well, let's graph these 5 points. So -2, 4. So you go left 2 and up 4. So this is your dots. -1, 1. You go to left 1, up 1, and this is your dot. 0, 0, again, is easy. It's right at the origin. 1, 1, it's going to be right 1, up 1. And then at the end, 2, 4, you go right 2, up 4. Now you notice that these 5 points do not fall on the straight line. It's going to be a curved line. So we're going to try our best and draw a U shape. Now, I don't want you to connect each dot using a straight line because it's going to look weird. So you're going to try your best. You use the most artistic skills to kind of just make a turn between each point. So it should look like a U shape or like a happy face in this case, okay? So it should be a U shape, not a V shape. And then at the end, again, you're going to make these 5 points larger, so that way you could memorize the locations of these 5 points. Okay, so these are the 5 points. Then at the end, you have something called an absolute value function. So whatever numbers you put in the absolute value, it's going to be positive. That's why it's called absolute value. You're going to make everything positive. So when you have an x is negative, so when x is -2, you put -2 in an absolute value, that just becomes +2. Likewise, when x is -1, you put -1 in an absolute value and it becomes positive. And when x is 0, since 0 is neither positive or negative, it just stays at 0. And when x is 1, absolute value of 1 is just same as itself 1. And at the end, when x is 2, you find what's absolute value of 2, and it's going to stay as 2. So you're going to plot these 5 order pairs. So negative 2 comma 2, you go start from the origin, you move left 2 up 2. So it's right here. Negative 1 comma 1, it's going to be left 1 up 1, which is right here. Again, you also have 0 0, which is right in the origin. 1 comma 1, that's easy. You go to right 1 up 1. And at last 2 comma 2, you go to right 2 up 2. Now again, this is not a straight line, but it is a V shape. So you're going to use a ruler and connect these 3 dots together, so to make it one straight line, and then you're going to connect these 3 dots together and make another straight line. So this is how an absolute value functions look like, the parent function of absolute value. So you're going to make these 5 points larger. Now these 5 points have a special name. You notice that every single parent function has 5 points, and it's always going to be the same 5 points. These are called the anchor points. I'm going to type it on the screen. Anchor points of a parent functions. So for linear functions, the anchor points are always these 5 points, and some of you like to remember where are they at, or some of you just like to memorize the table, and it's really up to you. You just have to memorize it in the future when you go to higher level math classes. Likewise, for quadratic functions, you have to memorize these 5 points, so that way you could generate a lot more quadratic functions. And then at the end, absolute value functions, same thing. You have these 5 anchor points, and it just looks like a V shape, so it's one of the easier graphs to remember. At the same time, you also notice that I keep calling these parent function. There's a nickname. It's mother function. It sounds like you're using profanity in math, which is totally fine in class, in math classes. So again, another way to say parent functions are mother functions. So we learned these 3 mother functions and learn how these 3 mother functions look like. And that's something you have to remember, or you're going to use for further in this lesson. So what's the whole point of learning these mother functions? Well, if you know how their parent function look like, and if you memorize these 5 anchor points for each parent function or mother function, you're able to generate a lot of graphs from these parent functions without actually doing math at all. So I'll give you an example. The first thing that we want to learn is we want to learn how to translate, in other words, move these 5 anchor points into different directions. So what translation says that if you have a parent function or mother function, if there is a number inside the parent function, if it's positive, you're going to move all the dots to the left, and then if it's negative, you move all the dots to the right. And likewise, if there's a number outside or after the parent function or mother functions, if it's positive, you're going to shift, translate those anchor points upwards. And if it's negative, you translate those anchor points downwards. So positive, negative, kind of, same as what we learned in the past for, from elementary school or middle school. But for left and right, you notice that the sign kind of reversed. Usually for right, it's positive, just like a number line, but in this case, it's reversed. So negative to the right and positive to the left. So you're like, I'm not still quite sure what does it mean. So let's take a look at some examples while keeping this paper on the screen as our cheat sheet. So I'm going to move this paper away. So let's take a look at example 1, and the title of example 1 is translation. Well, in part A, it says f of x is equal to x minus 1 quantity raised to the second power plus 3. Well, first, step 1 is we have to recognize, well, which one of these mother functions belong to this equation. Since I have a square, I'm going to find the name that has a square in it. Well, it's going to be this one, the middle one, because it has a square and it's quadratic functions. So step 1, it says graph the anchor points of the parent function. Well, so what you're going to do is you're going to copy these 5 points, 1, 2, 3, 4, 5, into the graph. So I'm going to copy negative 2, positive 4, so right here, and then negative 1, comma 1 right here, and pretty much you just have to copy these 5 points. Now do not connect them, because you're going to use these to show work. Well, first, I see that there is a negative 1 inside this mother function. So since it's negative, according to our notes, it's going to be 1 unit to the right. So this negative 1 is to the right. And then at the same time, I have a plus 3. And this 3 is outside the mother function, outside the square. Since it's positive, we're going to move all the points 3 units up. So that means you're going to move 1 right, 3 up. So let me write it down. So my translation would be 1 right, 3 ups. So what you're going to do is you're going to move all these points 1 right, 3 up. So let's start here. You move 1 right, 3 up. You have to count it correctly. Now, when you put a new point, I want you to use a different mark. So since I used dots for the first 5 points, maybe my next set of 5 points, I'm going to use a cross. So that way you're not confused which one of these points are the old ones and which one of these are the new ones. So I'm going to use a cross. Well, I did this one already. So the next one, this dot right here, I'm going to go 1 right, 3 up. So this is the new dot. And then at 0, 0, I'm going to move 1 right, 3 up. And then this is the third dot. Then on the fourth one is right here. I move 1 right, 3 up, which is kind of overlap, and that's okay. And then the last one was right here. Again, I move 1 right, 3 up. So I'm going to end it up here. Look at, don't you see another happy face? It kind of just translated here, right? So originally it's at the origin. Now I'm going to shift a little bit towards up and right. And then at the end, all you have to do is plot them. It's just connect them together to make it a U shape or a happy face like this. So this is a very shortcut to graph what we call a families of functions. So since these are parent, anytime you add a number to it, those are called the families of functions. I'm going to put that on the screen. So these ones are the parents of the mother functions, and then anything you add and anything that has a number in it, those are called the families of functions. So how many family members does each mother function has? Infinitely many. There's countless of them. Okay, let's take a look at part B. Part B is this absolute value of x plus 2. So out of these 3 mother functions, it's going to be the last one because the last one is an absolute value. So same thing is a step 1, graph the anchor points of the parent functions. So I'm going to copy these 5 points just quickly. Now once you did this many times, you kind of know the location of these 5 dots without even doing math at all. So it's kind of like an art class to you. Now since there's only one number and this is a positive 2 inside this mother function, it's going to be 2 units to the left. So all you have to do is move these 5 points 2 units to the left. So let's take a look at that. So I'm going to start with this point. I'm going to move 2 units, 1, 2 to the left, right? So 1, 2 like this. I'm kind of running out of space. And then here, same thing, 1, 2. And then here, same thing, 1, 2. And here, same thing, 1, 2. And here, same thing, 1, 2. So you notice that this V shape kind of shifted to the left 2 units to the left. And it's that the shape is going to stay the same. Kind of like how you learn in middle school. Every time you have a translation, it does not change the shape and size. It just moved to some other places from its starting point. So this is the graph of absolute value of x plus 2. Let's try one more, which is this one. C, h of x is equal to x plus 4. Now for this one, I don't see squares, I don't see absolute values. So out of these 3 mother functions, it's going to be the first one. And now some people get confused. They're like, well, is this 4 inside or outside the mother functions? It does not matter. Let's actually call it outside. So this 4, since it's, after the x, is going to be 4 units up. Okay, so it's 4 units up. So first graph these 5 anchor points, which are these 5. I'm just going to plot them really quick. And then after that, just shift all these points 4 units up. So let's see what happened. So starting here, 1, 2, 3, 4. Put an x. Starting here, 1, 2, 3, 4, put an x. Starting here, 1, 2, 3, 4, put an x. Starting here, 1, 2, 3, 4, put an x. Then starting here, 1, 2, 3, 4, put an x. So you notice that those 5 dots is translated 4 units up. And it's going to look like this. And then I'm going to connect it using a straight line like this. Okay, so this is the graph of h of x equals x plus 4. Now, some of you may get confused. They're like, well, what happened if I look at this 4 accidentally as the inside of the mother function? Well, then wouldn't that be 4 units to the left? Let's take a look at that. Now, if you start from the middle, and if you want to move 4 units to the left, hey, aren't you on the same line of the previous answer? Same thing. If I move this dot 4 units to the left, 1, 2, 3, 4, hey, it's the same line anyway. So for linear functions, this 4 could be viewed as inside or outside. But for every other parent or mother functions, well, they're pretty obvious. Like this 2 is inside the mother function, this one is inside the mother function, and this 3 is outside the mother function. Okay? Well, the next thing I want to teach you is after translation, we're going to take a look at reflection. Reflection means reflected upside down, right? So whatever on the top of the graph, you're going to reflect to the bottom. And likewise, whatever at the bottom of the graph, you're going to reflect it to the top. So for reflection, every time you have a negative in front of a mother function, and it's like a multiplication of a negative, then it's a reflection over the x-axis, so aka upside down. And we're going to take a look at some examples that involve reflection, okay? So let's take a look at example 2, which the title is reflection. Well, in part A, it says if you have a of x equals negative x squared. First, you identify the mother functions, which is the middle one. And your first step is going to be the same. You're going to plot the 5 anchor points, which is here, 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 and here, right? And then from there, since it's negative in front of the mother function, you're going to use the x-axis as a symmetry line and then reflect everything upside down. So your happy face will become a sad face later. So let's take a look at that. So this dot, I see that it's 1, 2, 3, 4, 4 units away from the x-axis. So at the bottom, you're going to do 1, 2, 3, 4. And you're going to put an x here. Likewise, this dot right here is 1 unit above the x-axis, so you're going to reflect to 1 unit below the x-axis. Now, since this dot 0, 0, it's already on the symmetry line, it stays the same, okay? And then this dot right here is 1 unit above the x-axis, so you're going to reflect it to 1 unit below the x-axis. And then at the end, since this dot is 4 units, 1, 2, 3, 4, 4 units above the x-axis, you're going to reflect it 1, 2, 3, 4, 4 units below the x-axis. And then at the end, you see that, well, these 5 dots are reflected upside down. So at the end, you're going to connect it. And this is the graph of negative x squared. In example B, what happens if you have the same, very similar functions, negative x squared but plus 1 at the end? Well, you're dealing with 2 things here. First, you're dealing with reflection, okay? And then after that, you're dealing with translation. Now this plus 1 is outside the mother function, so, and it's positive, so you're going to move 1 unit up. So you're going to deal with reflection and out. So what do you do? So step 1 is always grab the 5 anchor points. So it's going to be these 5 points right here. Okay, and then after that, now you're like, should I do reflection first or should I do up first, right? Now there's a difference in terms of the order. So you always, it's like Pam does, you do the multiplication first before you do adding and subtracting. So same thing, in transformation, you are going to do reflection always, and then after that, you move up, down, left, or right. So let's reflect it. Just like example A, you're going to reflect these 5 points at the bottom. So since we already did it in part A, I'm just going to do it quickly. So you have the second set of points. And then at the end, now you're going to create your third set of points now, your third set. So that means you're going to either use a different color or you're going to use another symbol, right? So in my case, I'm going to use a different color. So you're going to move the second set of dots 1 unit up. So since I use a cross, maybe after I move 1 unit up, I'm going to use a box. So I know that box is my third set of points. Likewise, since you have a cross here, you move 1 up, it becomes a box. You have a cross, move 1 up, becomes a box. A cross, move 1 up, becomes a box. And then a cross, move 1 up, becomes a box. And then at the end, you connect all the boxes. And this is your final graph, okay? Now on your homework, you have to show it like this. If I only see you having 1 set of points, I will mark it wrong and you will not get any credit. So I need to see different sets of points as part of your work. Let's take a look at more examples. In part C, you have negative x plus 2. So again, we have a reflection for this one. Reflection. And then this one is 2 units down, okay? 2 units down like this, right? Since this negative 2 is after the mother function. So first, we're going to graph the linear, these 5 anchor points. So you're going to have 1, 2, 3, 4, 5. And then you're first going to reflect it. So anything that's at the bottom of the x-axis, you're going to reflect it to the top like this. So these are the 5 new sets of points. And then at the end, you're going to shift all these second sets of points 2 units down. So if you have an x here, you move 2 units down, it becomes a box. Move units down, becomes a box. And then for this cross, move 2 units down, becomes a box. And then this cross, move 2 units down, becomes a box. And then for this one, move 2 units down, becomes a box. So you see that, well, it's going to be this right here, right? This final graph for the function negative x minus 2. Now, there's a quicker way to check it because look at that. You know how to graph this since middle school using slope-intercept form. Isn't the y-intercept -2? Hey, look at that. Isn't that -2? And isn't the slope -1? So hey, isn't this graph the slope into -1? So you could actually use your slope-intercept form to check your answer quickly to make sure that your answer is correct. Then at last, you have D, part D, which is j of x is equal to negative absolute value of x plus 1 minus 3. Same thing. Now this one has everything. So first you're going to reflect, and then this positive 1 means 1 to the left, and then this -3 means 3 units down, right? So same thing. First you graph the anchor points of this mother function. So you're going to graph these 5 dots, 1, 2, 3, 4, 5. And then after that, you're going to reflect them upside down. So since this is a V, you're going to draw an upside down V. So like this. That's your second set of points. And then at the end, you're going to move the second set of points 1 left, down 3, okay? 1 left, down 3. So for this cross, you do 1 left, down 3. And put a box. And for this cross, you move 1 left, down 3. And then for this cross, you move 1 left, down 3. And then for this cross, you move 1 left, down 3. And then for this cross, you move 1 left, down 3. Okay. You notice that again, it does not change the size and shape. If it's a V, when you do it upside down, it's an upside down V, and when you shift it, it's still an upside down V. The V is not going to change the shape and the size, and it's going to remain the same shape and size. So this is the final graph of this equation, negative absolute value of x plus 1 minus 3. So now that we learned translations and reflections, we're going to take a look at some homework problems so that you know the expectations of showing work and as well as checking the correct answers on your homework. Let's take a look. So on your homework, you see that there are 18 problems on this homework, and you're going to use the anchor points to show work before you graph the final answer. So at the end, I'll give you some selected answers for you to check your homework. But in the meantime, let's take a look at problem number 4 on your homework. It says f of x is equal to absolute value of x minus 3 plus 5. Well, I see that this mother function is the absolute value. So you're going to first plot these 5 anchor points. So I'm going to put 1, 2, 3, 4, 5. So you always start with the anchor points to show your work in this homework. And then after that, you're going to take a look at this -3, which is to the right. And then this -5, it's going down, okay? So for every dot, you move 3 right, 5 down. So 1, 2, 3, 1, 2, 3, 4, 5. You put a cross. And then from here, for this dot, you move 3 rights, 5 down. 1, 2, 3, 1, 2, 3, 4, 5, right? And then at the end, these 3 dots are going to look like this. And then at last, you're going to use a ruler and connect them. So that way, this is the final product of your graph, okay? You see that how I graph these equations without using table of values or using any math. All I have to do is use transformations, translations, and reflections. Let's take a look at some harder problems. For example, on the second page, I see that for number 16, let's take a look at number 16. Number 16 says, g of x is equal to negative, open parentheses, x minus 2 to the second power, and then plus 4. So I see that this mother function is the quadratic mother functions, right? So you're going to plot these 5 anchor points correctly. So these are the 5 anchor points. And then I see that since there's a negative, this is a reflection. So you're going to reflect these 5 points upside down. So it's going to look like this. So you're going to show work like this on this homework. So these are required to be visible on your homework. And then at the end, I see that there's a -2. So this -2 is 2 to the right. And this 4 is 4 units up. So for every second set of points, you're going to move 2 right, 4 up. So from here, you move 2 right and then 4 up. And it's very important that you use different symbol. Otherwise, everything's going to get messy if everything becomes a dot. So same thing for this dot. You move 2 right and 4 up. So 1, 2, 1, 2, 3, 4. And then for this dot right here, you move 2 right and 4 up. And then for this dot, you move 2 right, 4 up. And then for this dot, you move 2 right, 4 up. And then here is the final product of this families of functions. So I did 2 prompts with you. The rest is going to be very, very similar. I need to see anchor points at different set of dots before you draw on your final answer dots. And I will be checking on your homework, and I will show you the selected answers on the next screen. So that way you know the correct graph. Thank you.